Good afternoon, everyone. Folks are just trickling in, so we'll give another minute or two, and then we'll get started. Okay, we'll go ahead and get started. Good afternoon. Just a few housekeeping items as we get underway here. So if you have any questions, please use the chat feature in Teams to send a message, and I will do my best to answer those probably towards the end. And then also please note that the webinar will be recorded, and we will send a follow-up note with a link to the webinar afterwards. And I believe, although I may be mistaken, that you should have a link to this through Teams available to you afterwards. As a high-level agenda, what we'll cover today is just a brief introduction to Verist Engineering and a brief introduction to myself, your speaker today. I'll talk a little bit about the importance and applications of mixing and chemical reactions, where we find them in industry, and why we tend to care about that. We'll review some fundamentals of reacting flow, and we'll feed into how we model reacting flow. And finally, I'll share a few case studies in how we model reacting flow in two different scenarios. And we'll talk through how we go about setting up those models and the consequence of those choices. And finally, we'll end with some questions and answers. Okay, so my name is Mike Huron. I am a partner here at Verist Engineering, and I help to run our multi-physics simulation practice. I have a background in mechanical engineering, my PhD from the University of Connecticut, and in modeling of turbulent reacting flows. And I have spent the past approximately 20 years of my career helping clients understand, optimize, and design around the interaction of fluid flow, heat transfer, and chemical reactions. Now, Verist Engineering more broadly is a consulting company located in the Boston area of the United States. We are a collection of multidisciplinary subject matter experts, so PhD plus subject matter expertise in engineering mechanics, material science, chemical engineering, and electromagnetism. We help our clients accelerate product development and innovate in their toughest challenges through the application of engineering fundamentals and complex simulation. And we like to think of ourselves as providing academic expertise on an industrial timescale. As I mentioned, we're located just outside Boston. We were founded in 2006. We have 14 technical staff in our organization, 80% of which have PhDs. We have a 3,000 square foot mechanical test lab, which is focused on the testing and mechanical response of strain, temperature, and environmentally dependent materials such as polymers, adhesives, and foams. And that feeds and complements very much our multi-physics simulation practice. Verisk transfers all methods, models, and data to our clients. So we work in a collaborative fashion with our clients, and our clients at the end of our engagements own all IP that we may generate. So I mentioned briefly our practice areas, and from left to right, just to reiterate kind of the focus areas of our firm, starting with materials engineering. So we guide our clients and help our clients understand material selection and material trade-offs in their product development process, as well as helping to understand from a failure analysis perspective how materials may contribute to product failures, including when materials don't meet the spec that has been laid out due to, for instance, a vendor change. Our mechanical test and material modeling practice, again, focusing on software materials, is really built around understanding polymers, adhesives, and foams, with an eye towards developing and calibrating constitutive models that can be fed into finite element models. Our multiphysics simulation practice, again, which I help to lead, is a collection of experts in fluid mechanics, heat transfer, electromagnetics, chemical engineering, and solid mechanics. And we leverage best-in-class tools to help our clients solve really challenging, complex, nonlinear, and coupled multiphysics simulations. And certainly, chemical reactions and mixing fits that mold. And finally, our failure analysis practice, where we help our clients both in the industrial sector and our legal clients to help understand when something's failed, what is the root cause of that failure, and what potential remediation steps can be undertaken to help resolve those issues. Okay, so let's talk a little bit about why we actually even care about mixing and reactions. And the reason is that they're pervasive throughout industry. And just a few examples that we have listed here, spanning from the pharmaceutical industry, where mixing tanks are pervasive for the manufacturing and production of pharmaceuticals, to energy and green technology, where the mixing of reactants to generate energy or generate fuels is commonplace, as well as in chemical manufacturing for reactions to yield some desired quantity. And so throughout industry, we see chemical reactions and mixing playing an important role in key industries. And the interplay between these two effects, between mixing and reactions, affects a broad swath of these technologies. So from process efficiency and yield, which essentially is time and money, to product quality, to, in many cases, safety. And so understanding how these two complex phenomena interact is of critical importance to many product and process development activities. Now, when we have poor mixing in various reacting flows, that can have quite dire consequence. So, in one example of this is in a example such as steam methane reforming, where we are reforming to form, have a catalytic reactor to, in this case, form methane. It's the opposite of steam methane reforming. We may find that we get with poor reactor design and poor mixing of the constituents, we may get hotspots in our reactor that lead to potential thermomechanical failure modes. And so understanding how reaction proceeds, reactants and products mix can be critical to understanding potential safety issues and potential product durability issues. Beyond that, what is very frequent that we see in our consulting work is the formation of undesirable byproducts from selective reactions. So, for instance, in the energy production field, that may be pollutants. In the pharmaceutical field world, that may be intermediate species that are created due to incomplete mixing or insufficient mixing of the reactants. Now, beyond that, we see process inefficiency. So when we scale up from bench scale to production scale, we find what worked on the bench doesn't work in production, and we need to mix for much longer than we had previously contemplated. In one example, we have a recent client we worked with who, during their scale-up process, had something that mixed in 20 minutes on the bench. They expected a similar mixing blend time in their scaled up system and ended up with something that took 3 days. And so quite the expensive consequence when scale up is not done carefully. So the topic that we're here to discuss today is how do we use modeling as a tool to inform design. And modeling can be useful in a number of ways for process development and or scale up. And some of the key questions that we consider when we think about a modeling effort to inform a design of some chemically reacting system is, what is our critical performance parameter of interest? So is what we're interested in a global conversion rate? So in other words, A plus B goes to C, and we want to understand, what is the kind of macro performance of a device? Or do we care about something like reaction selectivity or intermediate byproducts that are perhaps more complicated to predict? Of key interest to that question is understanding how fast is the reaction. So we can often estimate based on rate constants and our known concentrations what we expect to be the rate limiting reaction step in our system. And then what can be a little more difficult to predict is how fast is the mixing, because mixing is generally going to be something that will vary throughout a device. For instance, on the right-hand side, we show an animation of the mixing of water and ethanol in a vortex mixer. And so you can see you get very strong mixing effects near the center of the vortex. You have a shear layer where the ethanol in red is introduced to the mixer. But at other places in the device, you may get slower mixing and more segregation. And so understanding the local behavior and the local distribution of mixing timescales and what physics are the rate limiting step can be quite important to understanding how to improve a design or operating parameters. And ultimately, that comes down to, is the quantity of interest in your design something where the local phenomena may matter? If every mixing time scale is faster than the reaction time scale, then the local details may not matter. But if you have some scenarios where you have parity between those two, then understanding the mixing distribution and how that interacts with the reaction becomes important. Now, it's important to note, especially in complex nonlinear models such as these, that all models are wrong, but some are useful when done correctly. And what we mean by that is that there's a lot of assumptions that we implicitly make when we set up a model. And often modeling every down to the molecular detail is not practical. And so as we make those assumptions, we understand that we're trading off accuracy for efficiency in terms of time. What I recommend and where we start when we study reacting flow systems is using global scaling arguments to make sure we're in the right ballpark. So understanding our reaction timescales, understanding scale-up heuristics from the literature, all of that can be very helpful to make sure we are in the right ballpark before we get too far. And when localized phenomena are critical to understanding process performance, then modeling becomes really an indispensable tool. Okay, so now that we've kind of covered a little bit of the background of modeling reacting flows and where that is important, let's take a step through the fundamentals and talk about the basics of chemical reactions and their governing equations. So as a first step, I'd like to point out that we broadly classify chemical reactions into two categories. So one is what we call homogeneous reactions. That's where we have all reactants and products share the same phase of matter. And so as an example of that, we show a simulation where we are predicting the effusion cooling near the wall of a combustor liner. And so here what we have is a flame that's indicated by the yellow and red contours. And so we have ignition and heat transfer to the wall of this liner, but everything in our system is of a gaseous phase of matter. Now, on the right-hand side, we have what's called a heterogeneous reaction. And so here we have reactants and or products that exist in two or more phases. And so as an example of that, we have a catalytic reactor used for steam methane reforming, where we inductively heat the catalytic particles, which are shown kind of in the center of this tubular reactor. And the reaction here occurs at the surface of the catalytic particles. Now, for the purposes of what we'll talk about today, we're going to focus on the homogeneous reactions, so the all gas phase or all liquid phase reactions. But certainly, if it is of interest to the audience, we can revisit the topics in the future. Now, in a reacting flow system, we generally must consider the system of equations that we show to the right. And so what we will be solving is the conservation of mass and momentum, along with the conservation of energy and the conservation of species. What we observe in this system of equations is that the very typically present various numerical challenges due to the very strong coupling between, for instance, the temperature and the reaction rates, the concentrations and the density of the medium, and the density, velocity, and pressure of the flow system. And in particular, what I've highlighted here is that reactions are often very strongly coupled to their thermal environment. So almost always you'll see reactions expressed in an Arrhenius type form, where you have an exponential term related to an activation energy and a temperature. And that strong coupling between the temperature and the reaction induces a very strong nonlinearity in these governing equations. So as we'll discuss over the next few slides, many modeling techniques are aimed at reducing or eliminating these strong couplings where appropriate. And that is kind of fundamental to any modeling exercise, is understanding where can we make assumptions that are reasonable to reduce nonlinearity in our reacting flow system. Now, key to reacting flows is understanding chemical kinetics. And what we mean by chemical kinetics is the pathway that reactants follow to get from their inlet concentrations to their product outlet concentrations. So in general, this conversion of reactants and products may follow complex pathways. Reaction rates are almost always nonlinear functions of species concentrations and temperatures. And what you'll see is many are reduced to single, what we call global one-step reactions. And so an example of methane-oxygen reaction is shown to the top right. It shows methane reacting with oxygen to form CO2 and water vapor. And while this looks very nice, it looks like a very simple one-step equation, it obscures many, many details that may matter depending on what the goal of our simulation is. Now, the detailed methane-oxygen reaction system is shown on the bottom right. And as you can see here, there are numerous pathways and many intermediate species. So whereas the top global reaction is just a single reaction with 4 species, the detailed mechanism or the detailed chemical kinetic pathways include 53 species and 325 reactions. So the natural question is, well, how well could we possibly know 53 species and 325 reactions? And for many processes, the answer is we really don't. And so using global or maybe a few step reaction schemes are much more useful and informative than complex detailed reaction schemes. But just as importantly is what is the question we're trying to answer? If we're trying to answer what's the overall heat release rate, or what is the concentration of major species such as CO2 and H2O, then a single step reaction may be sufficient. If we're trying to predict intermediate species like CO, in this case, carbon monoxide, then we'll need at least a reaction mechanism that includes that slower chemistry of CO formation and reduction to CO2. And so how much of the chemical kinetics we include is really a question that's driven by what is it that we're trying to learn from our simulation or our process analysis. Okay, so here comes the fun part. So turbulence is both a blessing and a curse. A blessing in the sense that it can be very, very helpful for reacting systems. The way that I think about this is reactions occur at the interface where the reactants mix, and that's reactants either mixing with each other or reactants mixing with the products. And turbulence acts to greatly enhance that mixing and interfacial area. For example, on the right, we show a very simple Bunsen flame. So on the very left-hand picture of the image, we see a laminar flame. You can see a very smooth and clear-cut interface between the hot section of the flame and the surrounding colder region. And as you transition to turbulence, the flame surface gets more and more wrinkled. So we're increasing the area of that interfacial region where reactants can mix and then consume to form products. As an example of how turbulence helps us, gas turbines and mixing tanks would need to be roughly 1,000 times larger without turbulence. So if you can imagine flying on a plane and your engine was quite a bit larger than the plane, that would be kind of how I think of the world without turbulence. So very beneficial from a process perspective. From a modeling perspective, makes our life quite a bit more complicated. And so the general reason is that comes back to the nonlinear nature of the chemical kinetic source term. So in most flow systems where we're modeling turbulent flow, we are using typically a Reynolds average Navier-Stokes approach, where we average either over time or period the governing equations, or for more complex flow systems, we use a large eddy simulation where we filter the flow field. And the consequence of that treatment of the governing equations is that we now have an unclosed reaction term. That unclosed reaction term shown on the bottom is the essentially the mean or the filtered reaction term. And unfortunately, it is not equivalent to taking the reaction term of the mean or filtered quantities. So we cannot simply do an averaging procedure on that reaction term itself. That ignores many of the details of what we call turbulence chemistry interaction. And we'll show a test case later in our slides here that makes evident why we have to use more sophisticated modeling approaches to capture the effect of turbulence on the reaction term and the reaction conversion rate in our simulations. So all of the computational modeling frameworks that exist in the literature and in the codes that you may use all are, for the most part, aimed at solving the problem that I just described, is how do we get at the mean reaction rate in a turbulent flow when we don't have all of the details available to us. And so broadly speaking, there are two orthogonal characteristics that we look for in understanding our reaction, our reacting system, and then therefore narrowing down how exactly we plan to model that reacting system. So the first is the rate of chemistry. So do we have fast reactions relative to everything else that's going on in our system, or do we have slow reactions? The other orthogonal to this is the reaction zone structure. So do we have a well-structured reaction zone? That means something like a flame propagation, for instance, you could consider a well-structured reaction zone, or a electrochemical reaction propagation, where you may have a wave propagating through a media. Or do we have more of a distributed reaction where there is no well-known or reduced order reaction that we can assume. So when we understand what our reacting system looks like, we can then use that information to guide us in selection of an appropriate method of modeling our reacting flow. And so to step through these briefly, in a scenario where we have fast chemistry and a distributed reaction, we typically think of this as mixing limited. And so that what that means is that as soon as the constituents or the reactants mix, they will, over some characteristic time scale, relax to their equilibrium value. And we can use this simplified modeling method to capture the source term and the interaction of turbulence and the reactions when one process is much faster than another. And so this is a very straightforward, assumes basically within the lifetime of a turbulence eddy turnover, the product will substantially relax to whatever their equilibrium value is. Again, basically just determined by the thermodynamics. Now, if we have fast chemistry, but we have a structured reaction, so again, think of the flame example, the premix flame or the flame propagation. Here, we can parameterize the reaction progress by what we call a reaction progress variable. So basically, that tells us it varies from 0 to 1, 0 being an incomplete reaction and 1 being a complete reaction. And we completely parameterize not just the reaction source term, but also all of the intermediate species based on that reduced order manifold. So now for something like that detailed methane oxygen reaction scheme where we had 53 species, we can reduce that into one equation that's purely parameterized by, for instance, a reaction progress variable. So this greatly reduces our dimensional space for simulation, and implicitly assumes that we can map the complex species distribution to a single parameter. Now, when we have slow chemistry or chemistry that is slow enough to be at parity with the mixing timescales, here we use a variety of approaches that directly resolve the chemical reaction term. And so, for instance, in a structured reaction, again, coming back to our flame example, we may use what's called a finite rate or a thickened reaction zone type of approach, where we solve directly for the evolution of the species and how they feed into the reaction term. And for a slow chemistry but distributed reaction, we may use something that is more sophisticated, like a transported PDF. Now, in a transported PDF method, I'll discuss in a little more detail later. What we're solving for here is actually the probability density function of the species distribution. So instead of solving for the species themselves, we solve for their PDF, and that implicitly captures the variation, so both the mean and the variance of those species distributions, and allows us to directly close the nonlinear source term in the governing equations. So this is a very powerful technique for capturing the interaction of turbulence and chemistry in where slow chemistry or slow reaction rates matter. Okay, so let's talk about how we apply these to some example systems that may be of interest. So the first question is, where do we start? And in our work, where we start is understanding the global values of our governing dimensionless numbers. So understanding the Reynolds number, which tells us whether the flow is going to be laminar or turbulent. That tells us what is the appropriate scale. That helps inform us what is the appropriate scaling parameters for us to understand mixing timescales. Then we'll try to understand what is the Schmidt number. So what is the ratio between momentum diffusivity and mass diffusivity? And in these scenarios, what we're looking for is, for instance, in liquid-liquid mixing, even when we have what seems like high Reynolds number, we may still yet have poor mass transport. And finally, understanding the Doppler number. So the Doppler number tells us the relative timescale ratios of the characteristic flow timescales versus the characteristic chemical kinetic timescales. And usually what we take for the chemistry timescales is the rate limiting step of our chemistry, which we can determine from the rate of reaction and our anticipated concentrations in that reaction step. Now, once we have a general sense of where our system lies, both in terms of our overall dimensionless numbers, we will next look to the literature to identify known scale-up characteristics. So, in many systems that are commonly encountered in industry or well studied, think the mixing tank or static mixers, and so we can take advantage of that. And at a very least, we can understand as a sanity check before we go into any more detailed modeling, what do we expect in terms of conversion rates or heat release, et cetera. And then when we have done all that and we seek to further understand local details, then we turn to modeling. So as an example of understanding laminar versus turbulent mixing, we talked just a moment ago about understanding what are the relevant mixing timescales that we want to consider. In laminar mixing, mixing occurs by molecular diffusion, which in general is quite slow. And that diffusion timescale is going to be proportional to the diffusion length squared divided by the diffusivity. And so in microfluidic devices, often what we'll see is the techniques to try to overcome the slowness of diffusion via chaotic mixing. So that could be by creating a serpentine mixer, which is shown on the left, or a herringbone mixer, which acts to stretch and fold the fluid parcels and enhance mixing. Now, turbulence, on the other hand, works by the breakdown of large eddies into progressively smaller and smaller eddies. And so we have macro and meso mixing timescales, which are at the device level or characteristic length of an inlet, for instance, and typically proportional to the turbulent kinetic energy dissipation rate. At the very smallest level, so as we break down these large eddies into smaller and smaller eddies, the smallest of eddies, either at the Kolmogorov scale or the Batchelor scale, are proportional to the mass or momentum diffusivity over the turbulent kinetic energy dissipation rate. So that's our most dissipative scales, and are essentially where turbulence meets molecular diffusion. Now, in a given turbulent system, our goal is to basically seek to make sure that the process kinetic times are slower than the longest mixing time, or in other words, that the mixing is faster than the chemical kinetics. But we need to understand the distribution of those mixing timescales, and as any one of them can be rate limiting in the overall process. So if we look at an example of this, here is what's called an impinging jet mixer, where we have ethanol coming in from the left, water coming in from the right, and they meet at a impingement plane in the middle of the mixer and oscillate and create turbulence based on that interaction. And so what we want to understand here is, where do we have these various timescales as we scale up this device that we need to understand and try to match between smaller scale and larger scale systems. So macro mixing is what we see in kind of the global scale of device level mixing or our bulk transport. Meso mixing is our vortex shedding and eddy size, where the eddy size are proportional to kind of a characteristic geometric scale, for instance, the inlet diameter. And then micro mixing occurs at our much smaller levels, at the dissipative scales, where the flow and the physics are governed by viscosity and molecular diffusion. Now, any of those can be rate limiting, and so what we do is we develop a way to look at where in our system are we limited by micromixing and where are we limited by mesomixing. And so, as you might expect, at the impingement plane and in the bulk of the main flows, what we're showing in blue here is regions that are mesomixing limited. And in red, where the turbulence is well developed, we are micromixing limited. And so using this as a guide, we can help understand strategies to, for instance, drive those mixing timescales down, and try to reduce the overall mixing timescale for our process efficiency. So now let's take this information and look at a few case studies that may be of interest, and put to action some of the techniques for modeling reacting flows. So the first is going to be our PCR diagnostic device design. So PCR, for those of you who are not familiar, refers to polymerase chain reaction, which is a technique for amplifying a specific segment of DNA to create millions of copies, typically for further analysis for detecting some sort of disease or other issue. And so PCR tests have obviously, I think, have been in everyone's front of mind over the past 5 years. But it's a common technique for doing this type of amplification of a particular molecule. It is, in general, a three-step process. First, a denaturing step where double-stranded DNA is separated into single strands by raising the temperature to around 95 degrees C. Then, in an annealing step, primers, which are short DNA sequences, bind to their complementary sites in the single strand at around 55 C, and then they are extended in the extending step to synthesize new DNA strands at a middle point temperature of 72 C. And the primary design challenge in these types of devices is to effectuate this thermal cycling between denaturing, annealing, and extending steps as quickly as possible. Essentially, we want the device to be as small and act as fast as we can while providing the proper DNA amplification to serve as a useful diagnostic. And so there are a few different ways people do this. One is what's called a shunting type device, which we see in the top right, where basically we have a droplet that is shuttled between the various temperature zones in a chip. Or something called a continuous flow device, which we show on the bottom right, where a droplet is continuously flowed, typically through a serpentine channel, through which manipulates the temperature of the droplet and takes the constituents through the three steps we just discussed. And so critical to this device design is balancing the thermal mixing and the reaction timescales. So here, what we'll look at is a continuous flow PCR device where we have the inlet up top, we have the outlet at the bottom, and we have 10 cycles through both a cold zone and a hot zone on the opposing edges of the chip. Now, these channels are drilled through a glass substrate, and which effectively carries heat from the heater to the glass channel. The channel is filled with oil, and a water droplet with the species is inserted into that channel and then tracked through the system. Now, we track the evolution in time of the 6 species shown in the table below, which evolve according to the the 4 chemical reactions that are listed in the inset. So if we look at the thermal response of the droplet, we can see as it traverses through the serpentine channel, at the bottom it becomes cold, and then at the top it heats, and all the while the reaction is proceeding based on those local temperature changes in the droplet. And so the reaction efficiency will ultimately depend on the residence time of the droplet within each temperature zone. So it has to essentially exist in the temperature zone for long enough so that the reaction can proceed in the various 4 steps that we just described. So if we look at, for a representative single step in the amplification cycle, what we're plotting here in solid are the 4 dilute species. So the double strand in blue, the single strand in green, and the complex of primers and extended single strands in black and gray. And in the dashed line, we have the temperature of the droplet. And so what we can see during the annealing step, we have the single strands concentration drops sharply. The primer complex concentrations increases sharply. We then get to the extension phase where the primer complexes both drop substantially, and then the double strand species increases dramatically before we get to our next denaturing step where the double strand is decomposed into two single strands, and we kind of start all over again by generating single strands to start the cycle again. Now, what you'll see from one step to the next is where we have a double strand concentration at the beginning of this cycle, which is lower than it is at the end of the cycle. And so this is the amplification that we are targeting. Now, if we use this model to understand, well, how does something simple like the flow rate affect our total amplification? That's what we're plotting here. So for various flow rates, blue being 2 microliters per second, which is our slowest flow rate, and gray being 8 microliters per second, which is our fastest flow rate, you can see in general, as we decrease the resonance time, we decrease the amplification of the double-stranded DNA. And so balancing both the desire for this to go faster with the need for the residence time to be long enough to sufficiently amplify the DNA molecules is kind of one of the key design challenges. And so we can further use this model to explore changes such as what is the droplet size, what's the channel cross-section shape and size, and what are the various temperature set points. Okay, so now let's switch gears a little bit, and where we just solve that with what we call a finite rate approach, where we directly resolve the temperature and the species evolution over time, and because it's laminar, there's no turbulence chemistry interaction. Now let's look at a slightly more complicated case where we have a static mixer. And what we use this case to demonstrate is the effect of reaction selectivity in a static mixer. So here we have flow coming in through the main channel up in the top and fed into a static mixer. And there being two side ports that feed a dilute second stream into that same primary channel. And so what we have in this configuration is a test case where we set up for parallel competitive reactions. So this is called the hydrolysis of DMP, where we have a reaction where one which is very fast, which is the neutralization of the acid, which is our K1 reaction. And we have a reaction which is much slower, which is the hydrolysis of DMP. Now, this is a great test case because what it shows us is when K1, or the first reaction rate, is much, much faster than K2, it's a good metric for how well mixed the system is. So if the system is perfectly mixed, we should see no conversion of DMP at the outlet of the static mixer. That is, as soon as the HCl mixes with the primary stream, it should be converted into NaCl. But if we have poor mixing and the HCl can persist long enough to react with the DMP, then we should see some conversion of that at the outlet in the by seeing acetone in the outlet stream. And so this reaction is really a great test case for understanding reaction selectivity and also understanding how our reaction modeling techniques can capture this type of behavior. So here, what we're going to do is compare two different modeling approaches. The first being the finite rate model. So that's the same model that we just used in the laminar system. We assume that there is no effect of the turbulence chemistry interaction. So the fluctuations in the species concentrations are negligible. Essentially, what that means is that we have perfect mixing at every cell in our CFD model. And we just integrate the reaction term according to its Arrhenius rates, again, ignoring the presence of turbulence. On the other hand, we use what's called the transported PDF model. And here, what we're solving for is the joint probability density function of the species. And when we recast the governing equations as to solve for the joint PDF, we get the equation that's shown under the second bullet. And so this is a transport equation for the PDF. And what's nice about this equation is that everything on the left-hand side is closed. That means we can solve without assumption the terms on the left-hand side, which critically includes the reaction term. The trade-off there is that we have to solve we have to model the terms on the right-hand side, which are the turbulent fluctuations of velocity, as well as the diffusion, turbulent mixing term. And those are also similarly complicated, but generally not as challenging to approach as the highly nonlinear reaction term. So let's take a look at how these two models compare. And so what we're showing here, is a comparison between the PDF method, which is in black, and the finite rate method, which is in blue. And in general, what we observe is that the finite rate method, where we ignore the turbulent fluctuations, greatly underpredicts the DMP conversion, especially at lower Reynolds numbers. So when we have slower mixing, what we would expect and what's supported in the literature is that we would have greater conversion of DMP. Basically, the slow reaction still plays an important role at lower Reynolds numbers, but we miss that completely with the finite rate method. Conversely, the PDF method does capture that, and this therefore shows that when we're approaching this modeling of a turbulent flow system of competitive reactions, capturing the effect of those fluctuations is critical for reliable understanding of how the reacting system proceeds. Okay, so with that, we'll just kind of quickly summarize what we covered today. So I gave you a brief introduction of who we are at Verist Engineering, an overview of the importance and applications of mixing and reactions, a review of our basic principles, and we talked through two case studies that show how we model some interesting systems that showed slightly different variations on the balance of mixing and reaction in PCR device and in a static mixer. And at this point, if anyone has any questions, I'd be happy to try to address those. Okay, well, I don't see any in the chat, but I greatly appreciate you all spending some time with me this afternoon. If you do have any questions, please feel free to reach out to me directly. Let me scroll back up to, my email address on the first slide. Would be happy to continue this conversation offline, and of course, help with any reacting flow modeling needs you may have. So thanks again, and hope you all have a great rest of your day.